Hi there, and welcome to today's lesson for BCIT Technology Teacher Education 5060. This is a course where we're going to be taking a look at tethered mini sumo robots, robots in general, and a large part of that is the motors and mechanisms that make these robots move. And to do that, you need to understand a little bit about well, DC electric motors and how they perform and where they get their power from. Now, as I was saying, these are DC electric motors, and tucked away right up in here under this corner, right underneath me, so just off to right there. There's a little red box that says permanent magnet brush DC motors. And well, with this video format, I've got it covered up right on here. But that's the type of motor that we're going to be talking about. And as you can see from the chart, there's all sorts of other motors that exist. There's AC motors, which use an alternating current that come in, and you can identify the AC motors usually because they'll have the RPM stamped on the side of the motor. So all those motors that you see down in the shop that say that they're an 1800 RPM motor or a 3600 RPM motor or however many RPM, that's because they're most efficient, their optimal, their design rotational speed is determined by the frequency of the current that is being applied to them. So in North America, we've got 60 hertz frequency coming into there. If you were to take that motor and plug it in Europe where they run at a 50 hertz frequency, then you would get a slower motor. You'd probably also blow it up because they use a different voltage, but hey, that's up to you. So AC motors, you can immediately pick them out because by and large, a lot of those will have a fixed RPM written on them. Not all of them will. There's, as you can see, many, many different types of motors, and they're all wound slightly differently to make them work. Now, over on the DC motors, which is the ones that we're more looking at because they run off batteries, so they're good for portable applications, you can see that there's all sorts of different windings as well. And you can get into the synchronous motors, which include stepper motors, which are actually really useful and require a little bit more control. And also a motor type that's becoming a lot more popular in small electronics and robotics application. And those are the brushless motors. And the brushless motors, just like the stepper motors, those require a fairly fancy external controller. You can't just go and hook a brushless motor up directly to a battery or hook a stepper motor up directly to a battery. Those do require control circuitry. And in fact, in a sense, that control circuitry ends up turning your control signals, the power that's going to drive the motor, into an AC signal, which is why you also see these covered down here as actually an AC type of motor. The motor itself is a synchronous AC motor, but the power that drives it comes in from batteries as DC, runs through a controller to operate this brushless motor. So anyways, there's a whole bunch of different ways to make an electric motor, and we're going to talk about one type, the permanent magnet brushed DC electric motor, because that is the least expensive and most common way to get a small amount of power for your small robot. Okay, so don't think this is an exhaustive coverage of every motor that's out there. This is taking a look at the one you're going to see the most in your high school shop in this application. So this doesn't apply to the big AC motors that are running your lathe or running your drill press that have an RPM stamped right on them. This applies to the little DC motors, this kind of thing right in here that we're going to be using with our robots. And when you take one of those motors apart, you'll see that they've got some fairly common features on them. And if you've ever built your own DC motor, you can do this reasonably easily. It'll be a gutless power, not very powerful little thing, but you can actually get something to spin fairly easily using these techniques. And there's some terms in here that describe what's going on. Now, in here we've got field magnets, and when we call this a brushed permanent magnet, DC motor? Well, in here, the field magnets are your permanent magnets. So these can be a rare earth magnet, they can be a ferrite magnet, um, but they're magnetic. And you'll have a north pole on one end and a south pole on the other, and a north pole on one end and a south pole on the other. And this creates a magnetic field. Now, using permanent magnets is different from a lot of heavier duty motors. Larger motors will tend to replace field magnets with coils in here because the more current you run through the coil, the stronger the magnetic field you can generate. So just because we're using a permanent magnet motor doesn't mean that all motors are permanent magnet. And in a lot of motors, you're going to see these replaced with coils to generate stronger electric fields, but not for the little motors that we're talking about and that we're going to be working with here. Now, inside your magnets, inside the motor, you are going to have a rotor. Okay, and the rotor is the part of the motor that rotates. So rotor, rotate, spin, whatsoever. And on the rotor, you are going to have coils of wire right here. Now, the core of the coil will be this laminated little piece of steel coming out right here, and that is to help direct and control the magnetic field that's being generated by electricity flowing through this coil. So this generates a magnetic field, and it'll create either a north pole or a south pole right here. And this rotor has been turned so it fits just inside the field magnets. So you get things very close together and get a good interaction between your electromagnetic field and your permanent magnetic field. Now, it's really important that this is an electromagnetic field because you need to be able, in order to get spinning, you need to be able to collapse, and I expand my hands. You need to be able to collapse and expand that magnetic field. And in fact, you need to be able to not only collapse and expand it, but you need to be able to switch it from north to south and then back to North Pole again so that we can switch whether this magnet right here, the electromagnet, is being attracted to this end of the permanent magnet or that end of the permanent magnet. And to do that, we have a commutator right here. And on the commutator, you'll see that there are brushes that contact the commutator. And this is why we call this a brushed permanent magnet DC electric motor. And these brushes right in here rest against the commutator. And as the motor starts to spin, the commutator spins within there and it goes from one brush to the other. So this will be your positive up here, or maybe it's your negative. This will be your positive here. So electricity will come down here. It will flow in perhaps through this side of the commutator, come out and activate this coil, and then flow out the other side down here to your negative side of the motor. Okay, as the motor spins, now where the power used to come in on this contact right here, it's going to come in on this contact and it's going to come out on another one, changing the direction of electric current flowing through the coil, changing a coil from either north to south to possibly an off state. Okay, and that is what's going to cause your rotor to spin within this magnetic field. Okay, so it's a really simple little device. And if you take apart a damaged brushed permanent magnet DC electric motor and take a look inside there, this motor that I've shredded apart right in here costs maybe $2. Look at the detail of work that goes into creating something like this and allow yourself to marvel that there is a process that allows something so complex, so sophisticated, so tiny. Just the fact that we can generate that much copper wire for $2, is this amazing thing. The fact that we can generate magnets for $2 and put them inside a steel case that we can make. The permanent magnet DC motor is really an amazing way to get a small, inexpensive device that generates movement based on fairly simple electricity. So, okay, let's take a look right here. Some of the key things that are good about this, these motors are usually small, okay? Less than 1 horsepower, less than 750 watts, usually less than a couple hundred watts. And the reason that they're small is because they're not a particularly efficient motor. So as soon as you start to get to bigger motors, the power waste that we get from going through the brushes and the risk of sparking right here, the fact that you can saturate the magnetic field right in here and you need super big magnets and super powerful permanent magnets, all of those start to speak against using this for really powerful motors. So Tesla isn't going to stuff one of these motors into your brand new Tesla. They might to drive the window up and down or to tilt the direction of the mirror or something like that. But they're not going to be using something like this to drive the car. Okay, those motors are just so big that rather than the inexpensive nature and simple nature of construction and operation of this motor, you get a much bigger financial return by the higher efficiency that you can get from going to a more efficient construction. One of the things that's key for us for using these inside our robots is that this is reversible. So as I was saying, you could run positive in here and have it come out this way and your motor will turn in one direction. If you reverse the direction of the electric flow, then the motor is perfectly fine with that. It will just spin in the opposite direction. There is sometimes a preference for motor direction depending on how the timing of the brushes and the commutator are set up on there. Generally, that is so insignificant that we can say that a brush permanent magnet DC motor will spin exactly the same in one direction as it will in the other. So there is no correct side to hook positive up to here. In fact, the correct side to hook your positive up to is the one that makes it spin in the direction that you want. That's a bit of a generalization. Like I say, there can be some motors that have unique timing that make them spin slightly better in one direction than in the other. But for most of our applications, if you're worrying about something like that, you're not watching this video because you already know what you're doing with it. That's a pretty fine detailed point. Most motors are perfectly happy and close enough to equal in each direction that it makes no difference whatsoever. Now, another thing that makes these really useful for our purposes is that they're really easy to use. The speed of the motor is controlled by the voltage, and the direction of the motor is controlled by the polarity. So we can create an H-bridge circuit and control it with pulse width modulation techniques that we'll talk about in later videos, but fairly easy to do with a microcontroller. And they just make it really, really simple. It's a solved problem for making your microcontroller or even just simple switches control your brushed permanent magnet motor. And again, as I said, you're limited by the strength of the magnets, but for what we're doing, I think we're going to be just fine. And we're subject to wear on the brushes. So right here, where things are spinning around, if you were going to design something to go into your new Tesla car and you were expecting it to last 20 years so that you don't have recalls and warranty returns and all that, you might not want brushed motors on there if it was going to spin a lot. But most of these are subject to occasional use and they turn on and they spin fine and they last a long, long time. In permanent, long-term industrial applications, this can be a wear point that's a problem. But if you're running your little robot 1 or 2 minutes at a time, and this is going to last you 20 or 30 years, no problem at all. Something else will kill it first. So there we go. The brushed permanent magnet DC motor, really, really useful motor, and we use them a lot. They are slowly being replaced by brushless motors in some of the higher power, higher end applications for educational robotics. But these are going to be relevant for a couple decades to come. Yeah, I know. Bill Gates said that 256K was enough for anyone. Wikipedia has a great explanation on these motors, and I've stolen an animation from them and provided you the link right down there. And go ahead and take a look at that. But basically what you see happening in here, very simple brush DC motor. We want it to spin around this way. There's our commutator, there's our brushes. Positive comes in this way, and you can see it's creating a north pole on this side. We've got a north over here. That repels. There's a south on this side. That repels. The motor spins around. Here comes that split in the commutator right there. So you can see that that's coming along right like so. We've still got the negative pole right up there, the north pole's here, so it's being attracted over to the south side. The south side's being attracted over to the negative. The north, sorry. And then as it spins around here, you can see that little split on that half of the commutator. We're about to swap the direction of electric flow through that coil. So now this is spinning this way, and the momentum of the rotor has driven it over into this side, and it's started to overcome the strength of that magnetic field. And right as it goes about another 10 degrees of spin further, then that magnetic field is going to switch. And we're going to go back to this position over here, where now this one is going to switch from being a south and being attracted here to being a north and being repelled from here. And that motor is just going to keep spinning around like it does in this little animated GIF right here. So anyway, you've probably seen animations and videos like this before, but it is worth taking a look at how we can get this little miracle of a $1, $2, $3 motor that actually spins around. It's really cool that it works. Now, we are talking about coils in here, and let me just drag this down here because I've got this lovely picture of coils right up there. There we go. Coils, inductors. And we've talked about them in previous electronics classes. And as you'll recall, electricity flows in through the one side of the coil, and it flows through all the wraps or turns on the coil and comes out the other side. And you can have some coils that have very many turns. So over here you can see there's lots and lots of turns of fine wire going around here. Here there's fewer turns, but of a coarser wire. And here there's like 2 turns, but of a fairly heavy wire. Okay, now keep in mind that there's a couple things involved in creating that magnetic field in the coil. And one of them is how much current is flowing through the coil. Okay, and the other one is how many turns that you have. So how many times that current flows around that coil. So if our electricity comes in right here and we've got 1 amp coming through here and it cycles around 1, 2, 3, 4, 5 times, that's the same as if you had 1 wrap carrying 5 amps. Okay, now down here you can see that we've got a lot more turns, but we also have a finer diameter wire. Okay, so that finer diameter wire can't carry as much current, but it doesn't have to because it loops it around many, many times. Now, what you can think about in terms of motors, you'll see motors have different voltage ratings that they like to run at. And generally what you'll find is that for battery applications, we tend to have the lower voltage motors. Okay, because batteries tend to be lower voltage than what you get from a power supply. Excuse me. And so if you've got a low turn motor, it'll tend to have heavier wire in there. And what that'll be for is so that you can carry more current through the wire, okay? And then with more current, you'll be using current to create that magnetic field. For a higher voltage motor, you'll have something more like this with lots and lots of turns of a smaller diameter wire. And that combination of the additional turns plus the length, so you've got length of wire in there, plus it's a really narrow diameter. As you do that, the resistance of your coil starts to go up. So you need a higher voltage to push current through there. So if you've got a motor with a higher number of turns, it will respond better to a higher voltage at lower current to get the same amount of power. And if you've got a motor with a fewer number of turns, you'll tend to have a larger diameter wire on it and fewer turns, so you'll more rely on current to get your power. Remember that voltage times current is your power. Power equals VI. Okay, so you can trade off one for the other. Generally, if you had to choose, you probably want to go to the higher voltage side of operations because when you're moving a lot of current, that generates a lot of heat unless you've got a very, very low resistance load in the, or load very low inductance coil. Okay, so inductors create a magnetic field about the coil. Now, again, just like it takes a while to charge a capacitor or discharge a capacitor, it takes a while to charge or discharge a coil. It takes a while for that magnetic field to expand or collapse or switch over to negative about that coil. And this brief resistance to current flow actually looks to the power supply that's trying to drive it a lot like resistance. And in fact, we measure it in ohms and it's called impedance. And if you get into electrical engineering, you'll do a lot of calculations about impedance and how it works and how fluctuating signals do all sorts of neat things when they go through wires. Here you just have to know that that happens. You don't have to be able to calculate it. Okay, and so we were just saying that the more turns equals more inductance. It takes time to charge and discharge a coil. And this matters because in order to make the motor spin, as you saw in the previous animation, you need to charge and discharge the coils. And if you want your motor to spin fast, you've got to charge and discharge the coils very rapidly. Okay, and that's one of the things that you can charge and discharge it more rapidly if you're driving it with a higher voltage, and you can't do it as fast as if you're driving it with a lot of current because it takes a long time to get that current flowing and to slow that current down and then change the direction again. The other thing that can happen while this is all spinning around, particularly on brushed motors, is that you can create voltage spikes and noise in your power line that can affect your other electronics. And when I say noise, I'm not talking about the sound. You will sometimes hear a little high-pitched sound coming off your motor if you're trying to get it to turn and you're using pulse width modulation, but just not quite giving it enough current. That can be a sign that something's up with your PWM system. But really what you'll do is you'll see this noise as a random signal on your oscilloscope, and it'll be an electrical noise that can back into your system and affect other things. And you'll see sometimes people will take a capacitor and they'll come in and you've got motor terminals here and here on this little motor, and they'll just solder a small capacitor across there. A ceramic capacitor or a film capacitor, not an electrolytic, because electrolytics will be polarized and you're going to be changing the polarity all the time. So you wouldn't want to do that. You could risk blowing up an electrolytic capacitor, but certainly a ceramic or a film or a non-polarized capacitor of some type would be fine to put across there, and that would just help absorb some of those little noise shocks. It's not necessary in the circuits that we're going to be making, but if you see a capacitor across there, that's what it's there for and that's what it's doing. Now, something else you've probably seen about brushed DC electric motors is that they also work as a generator. So typically, you put electricity into the motor and you get motion coming out of the motor. But if you take motion and put it into the motor, you'll get electricity coming back out of that motor. And you have to spin the motor pretty fast to get any significant voltage coming out of it. It's just like it's not a really efficient way to turn electricity into motion. Far more efficient than something like a gasoline engine, but not nearly as efficient as a brushless motor or something like that. But this is not a particularly efficient generator. It works and it's cheap, and if you only need a little bit of power, or you want to experiment with something with your students, it works pretty good. But just know that you've got to get that motor spinning pretty fast, okay? And the quicker you turn it, the more voltage you get coming out of it. Now, and the less current you've got flowing, the easier it's going to be to turn. If you short your two terminals together right there, solder that one straight over to that one, it acts as an electrical brake, and you can actually try that. Take a motor like this and try spinning it, and then take little alligator clips and clip those two terminals together and try spinning it, and it feels quite a bit different. Um, and anyway, so we can use the motor as a generator, but what's really interesting is that you can use any power source to turn the motor, even the motor itself. Now, this is a little bit of a play on the mind. It's one way of describing what's happening. Um, and it describes something called back EMF. Okay, now EMF, electromotive force, is another word for voltage. And what we're saying right here is that when you spin that motor up, the motor starts to act as a generator and it pushes back against the incoming voltage. Okay, so if you're applying 12 volts to your motor and you hold your motor stalled like this so that it never spins, the only thing that affects the current flow through your motor is going to be the resistance of the motor. None of that impedance and stuff matters at all, because since the motor's not spinning, the brushes aren't going around. They're stuck, the commutator's not going around. The brushes are stuck on the same pieces. The coils are stuck. They've got time to fully charge and create their magnetic field, and just nothing's going anywhere. So none of those effects matter at all. As you start to let go of the motor a little bit and start letting it spin faster and faster and faster, now the motor is spinning, okay, and it's acting as a generator, creating a back EMF that pushes back against the voltage. So if you've got 12 volts applied to that, and that's a little bit much for this motor, but let's say you've got 12 volts here and you're holding it like this so that it's stalled and nothing's spinning, you're going to get your maximum current flow through there, because the only thing stopping the current from flowing through there is going to be the resistance. And the resistance of these coils, they're just copper wire. It's really, really low. So you're going to get a lot of current if you hold that stalled. And eventually the motor's going to heat up and start to smoke, and then the motor won't be so good anymore. So as you allow that motor to spin, though, just as if I was spinning it like this, oops, I think I stripped a gear there. Don't spin the motor quite that enthusiastically. These are inexpensive little gearboxes. As you spin that motor back, oh, definitely stripped a gear. Oops. As you spin that motor back and forth, what you're going to find is that it's going to generate its own voltage, and that voltage pushes back against the 12 volts. So now you're applying 12 volts to this, the motor's spinning, and now you've got 6 volts pushing back against that 12 volts. So the 6 volts that being generated by the motor spinning means that now if you're pushing back with 6 and applying 12, then you're going to get only 6 volts pushing current through the motor. Now, your current flow goes down because you've still got the same amount of resistance in here. You've just got lower net voltage pushing electricity through here. And if you allow the motor to come up to its full free speed, you could have 11 volts pushing back against the 12 volts and only really having one useful volt driving current through your motor. So your current will go down, even though your voltage being applied will stay the same. So this is kind of cool, that as that back EMF reaches equilibrium with your applied voltage, your motor will stop accelerating, and you'll reach your natural RPM for whatever torque load you have applied to the motor. And if you want the motor to go faster, you have to apply more voltage. Now, keep in mind, I'm talking about the average voltage being applied on here. By using pulse width modulation for your motor control, and we'll talk a little bit more about this later on, you can change the average voltage being applied to your motor. So if you have a 50% duty cycle, so say you've got a 12 volt battery at 50% duty cycle with your PWM, that's like having 6 volts applied to your motor. So you'd get the same motor speed as if you directly hooked up a 6 volt battery to your motor, and would have the same performance characteristics because your PWM would be turning on and off so fast that the motor would only see well, there's 12 volts on there, but it's turning on and off so fast, it's just going to average it out, and it's going to look like 6 volts. Just like with an LED, if you hit it at 50% duty cycle on the PWM, it's going to look like an LED to your eye. You're not going to see it flashing because it's turning on and off so fast, but it won't be as bright. Here, it won't be as fast. Okay, so voltage controls speed. The other key thing we've got to talk about is current. So what does current control, but it's more like a question of what controls the current. Now, keep in mind how we've got that rotor stuck inside the motor there and it's trapped in the magnetic field. And if we want to create more twisting force, more torque inside that motor, then what we need is stronger interactions between the magnetic fields. The only thing we can control as the end user of the motor is the amount of current flowing through that coil. The more current that flows through the coil, the stronger the magnetic field coming out of the coil, the stronger the interaction with the permanent magnet electric motor, and the increased torque that you get coming out the shaft. So more current equals a stronger magnetic field equals more torque. So your speed is proportional to the applied voltage. General rule on there. There's fudge factors involved, but basically if you run this motor at 3 volts, it will give you an output speed that is half of what you run it at 6 volts. And if you run it at 12 volts, it will spin twice as fast as if you run it at 6 volts. And if you put a 1 Newton meter load on here, the current draw will be half, approximately, because you've also got drag in the gearbox and everything like that. But if you apply a 1 Newton meter load on here, the current will be half of what you would expect if you were applying a 2 Newton meter load onto here. I pulled those numbers out of thin air. I haven't actually sat down and thought about whether 1 Newton meter or 2 Newton meter is even remotely relevant for that particular gearbox. So key thing is speed, voltage, current, torque. Okay, put those two together. Well, you multiply voltage times current, you've got power. But if you think about what you've done in your automotive mechanics class and all that, then you multiply your speed times your torque, and you also have power. Makes sense. Electronics, mechanics, coming together right here and meshing fairly nicely. Okay, so let's think about how this works for just a minute. So we want to get a motor running. We're going to apply 9 volts, and we're going to assume this power supply has, more current available to us than we need. It's a big 9-volt battery, not a little 9-volt battery, but something like 6 D cells all hooked up in series. Okay, so lots of current available right here. So unload motor, it's stopped. It's not spinning at all. It's turning at 0 RPM. And the term for not turning is stalled. Now, in this case, it's stalled because there's no electricity applied to it. It's got no reason to turn. At this point, there's no back EMF pushing against the applied voltage because it's not turning. So now we turn on the 9 volts. And at the very beginning, before the motor even starts to turn, because remember, electricity moves a lot faster than mechanics does, okay? All 9 volts from our power supply are used to push current through the windings of the coils on the armature. So all 9 volts are being used to expand that magnetic field and create the interaction between the rotor and the stator being our fixed permanent magnets. This creates some torque because now the motor wants to turn. It's got some twisting going on in there. The motor begins to spin. Okay, and this leads to a key point right here. At stall, anytime when your output shaft is not spinning, your motor will be at its peak torque, because it's got its peak current draw. Or you could say it's got its peak current draw because you're at your peak torque. Okay, but basically at stall, at 0 RPM, you get your maximum amount of torque. And this applies to a lot of different types of electric motor. Um, and it's one of the reasons why a Tesla kicks a Ferrari's butt in acceleration. Because in a mechanical engine, in an internal combustion engine, you get zero torque at 0 RPM. You've got to rev that motor up and get it spinning so that your 4 cycles of combustion can come through there and move oxygen in and burn it and expand and get the exhaust gases out. So you've got to be revving, you got to be up at 3,000 to 6,000 RPM if you want to get some decent torque, depending on your motor. If it's a diesel, it'll give you something. Anyway, we're not talking about that. We're talking about electric. At stall, electric, peak torque, peak current draw. Now, as the motor starts to spin, okay, it speeds up. Now, you start to increase your back EMF coming off the motor. And this pushes back against your 9-volt applied motor. So your effective voltage pushing the current through the motor is now your 9-volt power supply minus your back EMF. Your back EMF is proportional to your RPM. So as you increase the RPM, you increase the back EMF, and the effective voltage pushing motor through electricity through that motor starts to go down. This results in less current flowing through your motor, less current, less torque, so your motor accelerates more slowly. Now the motor will keep spinning faster and faster, and as it does, it draws less current and creates less torque. Eventually, you'll reach a point where the amount of torque that you're creating is just enough to get the motor to spin at the RPM that it's spinning at. And that will control the state of your motor. However, if the motor is completely unloaded, you're holding everything up in the air and you're just letting it spin so that the only thing slowing it down is the mechanical drag of the gears and the pinions or whatever you've got applied to your motor. Eventually, you're going to reach something called free speed, which is as fast as your motor can go at any given voltage. Of course, you increase the voltage, it'll go faster until you reach the point where you blow the motor up. But the free speed at any given voltage is when there's no load, when there's no torque being applied to the motor. So at freed speed? Well, I'm not fixing that typo right now. At free speed, the motor produces no useful torque, okay? Because as soon as you're producing a useful torque, that torque is going to require a bit of interaction in the magnetic field. It's going to slow the motor down a little bit. And now all of a sudden, you're not at free speed anymore. But it's got it. So when you're at free speed, you've got your lowest current draw on there, low because it's the lowest torque, and that's because you've got a high back EMF pushing back against the applied voltage, reducing the effective voltage trying to push current through the coils. Now there are alternative ways to explain this, and we can take a look at charging and discharging coils, and because the motor's spinning faster, you've got less time to expand and collapse the magnetic field. But basically you can think of it in terms of the back EMF pushing against it. We've got some charts that will help illustrate this a bit later on. So the motor was spinning at 9 volts. Now we come to our power supply, we turn the dial up a little bit, and now the motor's spinning at 12 volts. Okay, this just increased the effective voltage across the coils because our previous back EMF was somewhere around 8 volts maybe. Well, now we're applying 12. That motor's going to start to speed up again because we've got more current flowing through it, which creates more torque, which allows us to overcome more resistance in the system, and it can spin faster until the load on the motor, just coming from the bearings and the gears and everything like that, starts to slow it back down again. Okay, so now the motor's spinning faster because we're at the 12 volt free speed. Yeah, there's a lot going on there. Like I said, we've got a couple of curve graphs coming along that will illustrate that. And Then what we can say is, well, you're spinning at free speed at 12 volts. We put a little bit of load on the shaft. Okay, now the drag from that load starts to slow the motor down. That reduces the back EMF coming off the motor, increasing the effective voltage across the coils and increasing the current flow through the motor. As we increase the current flow through the motor, that increases the strength of the magnetic field on the rotor. So we get stronger interaction with the permanent magnets and we get more torque. Okay, some of that torque is still being used to overcome that armature drag that we were fighting with at free speed, but now some of it is doing useful work. And a loaded motor draws more current and spins more slowly than an unloaded motor. Excuse me. Okay. This gives us a very characteristic power curve for a brushed permanent magnet DC electric motor. And you'll see these power curves generated for a whole bunch of different motors. In fact, you've probably looked at power curves for motors when looking at internal combustion engines as well. The electric one's slightly different. You need to pay attention to a few more different things going on. But it's really useful, and it's actually really beautiful and pretty easy to understand once you take the time to know what's going on down here. This is a very, very useful and very, very complex drawing, and it took me a while to figure it out the first time that I saw it. First of all, you have to know that this is going to be for one specific motor at one specific voltage. And this is the motor that I used with my high school students when we were building electrothon race cars. And we ran off of a 24 volt supply, so two 12 volt gel cell, basically car battery size sealed lead acid batteries in series with each other, running through a speed controller. So the speed controller would turn on and off very rapidly using pulse width modulation, and it could give us a lower voltage than 24 volts if we wanted to, and it could bring us all the way up to 24 when we needed our maximum output. So we're just going to assume that this is at our maximum power output, that we're applying all 24 volts directly to the motor. And this tells us the performance characteristics of this motor when 24 volts is applied directly to the motor. Okay, now you need to take a look at the axes anytime you go to read a graph. And down here, we've got torque at the bottom. And hey, this was 20 years ago we were doing this. The motor was rated in foot-pounds. Most of the stuff you'll see now, the torque will be rated in Newton meters. Or hopefully it will. There's still this one country to the south of us, but you know, I think they've got bigger problems than metric and imperial right now. Like metric imperial is still a big problem, but oh, they've got a few things to sort out down there. Love them. They're friends and neighbors, but anyway, I wish them well. So foot-pounds, woohoo! Imperial units, straight out of the 1800s? Anyway, no, they had metric back then too. Anyway, power curve, specific voltage, find that torque along there. It's along the x-axis, and you can see we start at 0 on this side and go up to whatever our stall torque is going to be at this end, and we'll talk more about that in just a moment. And then on our vertical axes, we've got a number of different axes because we're measuring a number of different things on here. So for instance, you'll see the amps is measured in red and comes over here. The RPM is in blue, and it's measured on the blue line right here. Our horsepower, yay, Imperial, is measured in green and comes up around like here in a very characteristic shape. It's the only one that curves with a peak in the middle. And our motor efficiency also comes up in a peak, but it tends to peak. In fact, it will always peak to the left. This is my left. Anyway, this is the left of the drawing. To the higher RPM, lower current side of the peak power in here. Okay, so let's just take a look at some of the terminology that goes on right in here and how this comes together and how we read this chart. So in our last example, we talked about a motor starting at stall, okay? So here is our motor at stall right down here because the motor is spinning at 0 RPM. So find the blue line for your RPM right here, and at stall, 0 is right down here. So you want to intersect the blue axis with the blue line, and that puts us right down here. 0 RPM is at point A on this chart. Okay, now the state of this motor at any given point with 24 volts applied to it is given by the vertical line that intersects the horizontal axis. So at 0 RPM, we're at this point right here. And so we can find all the rest of our information by taking a look up and down here. Okay, so if we want to know how many amps are being drawn, we start at A because we said, okay, at 0 RPM, find the RPM, come down here till the point where RPM is 0, draw a vertical line. Now we want to know how many amps are flowing, find where that vertical line intersects the amps line. Okay, and that's right up here at point B. Draw a horizontal line at that point, you come over here, and this will tell you how much current the motor is drawing. C right in here, okay, 450 amps at stall is what this motor is going to be drawing. Now, we can also tell you some things about the power output and the efficiency at stall. And in fact, they're pretty simple to tell because if you look at where this vertical line intersects with your horsepower and your efficiency lines, within the margins of error, it intersects at 0. When your motor is stalled, it is doing no useful work. Your power output is 0, even though that motor is trying really, really, really hard to turn, it's not turning. It's not doing work. It's not creating mechanical power. You have 0 watts of mechanical power coming out of that motor. Now, you've got 24 volts at 450 amps going into that motor. That's a lot of power. 24 times 450, let me just quickly fire that up. 24, enter 450 times. That is 10.8 kilowatts of power. Okay, that's a lot. I mean, if you've done welding, you know what 400, well, you don't know what 450 amps looks like because you don't even weld with 450 amps. That is a huge amount of power going into there. And yet none of it's coming out as mechanical power. Well, where's it all going? Heat. You've basically got a heater. Anytime you have a stalled motor, you don't have a motor, you have a heater because it's generating no mechanical power. And so our horsepower, our power output, our wattage is at 0. And our efficiency, which is the ratio of our input power to our useful mechanical work coming out, is also at 0 because we're putting a ton of electrical power into there, and we're getting almost no mechanical power coming out. So at 0 RPM, this is a really bad place for your motor to be. You do not want to leave it at 0 RPM for a long time. Okay, so thankfully, you'll see that you're also getting a lot of torque. You're getting 22-ish, 21 and a half foot-pounds of torque coming out of there. And if you've got any kind of gear reduction at all, that's going to be creating even more torque at your drive axle. And this motor is going to want to start to turn. But if you turn it on and your motor's not turning, don't leave it there for too long because you're going to get a very hot motor and it's going to let the smoke out, or your power supply is going to let the smoke out. Something's going to go bad if you leave your motor at stall for too long. So So at stall, you've got zero useful output, as I was just saying, because torque times RPM is your rotational power, and if RPM is zero, then your power is zero. It's not moving your robot, and your efficiency is also zero on here. So we talked about that a little bit. Now, as your motor starts to speed up, things start to change, and it actually does stop being a heater and starts to become a motor. It's still a heater. It's just a lousy heater because it's actually partly a motor too. So let's take a look at what happens at 1000 RPM. Okay, so what's going on in this motor at 1000 RPM? Find 1000 RPM on the y-axis. So you got to come to your RPM side right up here. Okay, yay, RPM in blue. And come down to 1000 right here. Okay, there's point A. You can see point A right here refers to step A right over here. So when you're doing this a little bit later on and playing the home game, you can make that comparison right there. And draw a horizontal line right over here at 1000 RPM and find where that intersects with the blue RPM line. Okay, so 1000 RPM right here. Come over here. We want to know the state of our motor at 1000 RPM. So at point B, we draw a vertical line up and down right in here. Okay, now this vertical line describes the state of the 1 horsepower Scott motor with 24 volts applied to the terminals when it's spinning at 1000 RPM. And you'll notice that now our torque has dropped. Our torque at stall was up around 21, 22 foot-pounds. Now we're down to 15 foot-pounds. Okay, so we're not getting so much torque out of the motor anymore because we're spinning, but a few other things have changed as well. So take a look at the line up here and come up to our amps. And you'll notice our amps used to be really high, but now our amps have dropped off and we've gone from 440-ish down to 300 amps. Okay, which is still a lot, but it's not as much current. That's because the motor is generating back EMF and it's pushing back against those 24 volts that are being applied. Let's take a look at some of the other things that are happening in here right now. Okay, where's our power output? So again, we're looking at this vertical line representing the state at 1000 RPM, and our power output is now, it used to be right down here, our power output has now come up here. And we can actually, it's just coincidence that the power and the amps coincide at just about the same spot. That won't happen if we pick a different number on here. But we can come over here and we can say that our power output is 3 horsepower. And if we take a look right here, we can come up here onto our pink line and take this over and say that our efficiency at this point is about 30%. What that means is that of all the electrical power that we put in, 30% of it is actually coming out as mechanical power, 70% of it is coming out as heat. So we've still got a heater, basically. We did this a lot on our first vehicle. We geared up our motors too high. We said we wanted to go really fast, and our motors always ended up getting trapped on this side of the power curve because we were trying to draw too much torque from them and make the vehicle move with torque rather than making the vehicle move using RPM and gearing it down to get torque. So anyways, the motor starts to spin faster. We will hit this point called peak power. Now the peak power is the highest point on your green line right here, and in our case it comes in just a hair over 3.5 horsepower. Okay, now to find out what RPM that happens at, find your peak horsepower and draw a vertical line. We do a lot of line drawing on here. Okay, and if you take that vertical line right down here, you'll see that you're somewhere around 11 foot-pounds at point C. Okay, to find out what the other performance characteristics are, rely on that vertical line. Okay, if you want to know how much current is flowing, come down here to where it intersects with the current line that says amps, come over here, and you're somewhere between 200, 250. Okay, so maybe about 230 amps. If you want to know what your efficiency is, come down here. And again, we've got this little coincidence where we intersect with more than one line. Come right over onto this side. Now our efficiency's gone up to just under 50%. Okay, so when you're getting your peak power, peak mechanical power output, the motor's still not really efficient. We use the motors in a type of racing called electrothon racing, where you only got the two batteries to power your vehicle for an hour. So if you ran at peak power all the time, you were going to get your clock cleaned by somebody who found a way to run their motor at a lower power and a higher efficiency, because more of their power would be going into actually making the motor spin, and less of it would be going into creating waste heat. Yeah, so if you want to know what RPM you're at, again, draw that vertical line, find where it intersects with RPM, and point D is going to drag you right across in here and tell you you're around 1550 RPM, just a hair above that 1500 line. Now, as your motor spins faster and faster and faster, you will reach a couple of points. Now, here is on this drawing, you won't see this on everyone. They've got a line representing the rated load. And this is, like I say, a 1 horsepower motor. That means 1 horsepower continuous. You'll see that its peak power greatly exceeds 1 horsepower, but if we left it right there, we would be turning so much power into heat because we're running at low efficiency that we would bake that motor and we would burn the insulation off the coils and you would see smoke coming out of there and you would destroy your motor. If you want to run that motor continuously, you need to have your power underneath this rated load line. So you're going to be running in this region right here, and you'll see that the rated load, when you take that line across right there, intersect it with your horsepower line, comes over there, and that's the 1 horsepower rated load. And that means that if you're going to use the motor continuously in your electrothon race application where you're running it for an hour, you want to be on this side of that line. You want to have your power down in this range right here, which means that your RPM at the motor output shaft needs to be spinning at about 2900 RPM or higher. Okay. Now you can get even a little bit better if that motor spins a little bit faster, because somewhere right in here you're going to reach your peak efficiency, and that peak efficiency will come down. You can draw a vertical line right in here that would intersect right here, comes right over here at just above 3000 RPM. And once you're just that little bit above 3000 RPM, 3100, 3200 RPM at your output shaft, then follow your efficiency line right across here, and somewhere between 85 to 86% of your of the electricity that you're putting in is going to be coming out as mechanical energy. It's way better than we were doing when we were running at peak power right in here, and we were only getting less than 50% of our battery power being turned into electricity, the other 50% going into heat. Now we're up here and we're getting 85% of our power coming off as mechanical power and only 15% coming off as heat. Much, much nicer. Okay. So very useful pieces of information tucked into the motor power curve. Now, in order to get your motor spinning at the speed that you need, while still creating enough torque to twist your output shaft and drive your wheels, you need a gearbox. And just about every one of these little motors that you're going to use has a gearbox of some kind. On our Electrothon cars, we didn't have a custom-built gearbox like this. We just used a very small pulley on the motor shaft and a very big pulley on the wheel that we were driving. We were turning wheels on bicycle wheel sized, moped sized wheels. And so, we would have 10 to 1, 12 to 1 gear reduction just in the pulley right there. Smaller motors that spin faster. If you want output shafts that spin slower, you need more gear reduction right in here. Okay, so this is really important to understand because, like I say, we got stuck in our first test runs because we calculated how fast we wanted the car to go and just looked at the power without really understanding the chart. Yes, there was a time where I didn't understand the chart that well, and I certainly didn't understand the importance of the motor power curve chart. And after getting a couple of good butt kickings from physics out at the racetrack, we went back and we sat down and we figured it out and we studied it. And now I'm sharing the information with you, so you don't have to overheat your motors. Um, so most of the things we want to do require high torque but at low speed for a lot of our robot applications. And to do that, we need to use a gear ratio so that you can spin your motor fast but have your final output shaft go slow. And so take a look at the chart that we've been at, and you've got two ways that you could get 1 horsepower out of that motor. One of them is at the recommended side of things, spinning at 3,000 RPM. Motor's 85% efficient, draws only 50 amps of current, and generates 2 foot-pounds of torque. Okay? Or you could spin the motor 10 times slower, but get 10 times as much torque, and in the process draw over 8 times as much current at 1/10 the efficiency. Both of these situations generate the same amount of mechanical output power. One is on this side of the chart, and the other is on that side of the chart. Okay, you recall there's a power curve that goes up to the top and then comes down to the sides. You're going to hit one here and one here. Which 1 horsepower do you want to get? 85% efficient generally sounds better than 8% efficient. So what you do in this situation, instead of just putting the wheel directly onto the motor, you get that 10-to-1 pulley, okay, and 10-to-1 gear reduction, and spin your motor at 3,000 RPM, reduce it 10-to-1 in the pulley so you get 300 RPM. When you reduce the RPM, you increase the torque, okay, and you get 20 foot-pounds of torque coming out of here. You get the same mechanical performance as if you loaded the motor up really heavy, but way better electrical performance. Your batteries will last longer and your motors won't overheat. Now, there's a really cool website called geargenerator.com. So if you're having problems understanding how gears and pulleys work, because you know, it's maybe something you haven't taken a look at in a while, go to geargenerator.com and you can start playing with different gear ratios. In fact, I'll probably talk about that in a different video because I know some people get stuck on it, particularly with our little gearboxes here where we've got one gear driving another gear on the same shaft, driving another output gear, but we'll take a look at that later on. Now, specific to your Mini Sumo, and you're going to be, and also similar to this, these tend to have a motor that we'll call the 130 motor. And there's different turns that you can get for these. So the motors can be spun up differently, so that that there's different numbers of wraps around around each pole on the rotor. And so you can get different motors inside the same case, and that's a fairly standard thing. So you pay attention to what you're looking at, but this is the closest to the power curve that I could find for your little tethered Mini Sumo robot's power curve. And I've included this in a handout that I've given to the class called the Mini Sumo Design Tips. And I go through the calculations of how to use this information to figure out what size of wheel you want to have for your robot with what gearing on your robot, because you're going to need to understand that pretty well in order to design your robot, because how do you know how big to make your wheel if you don't know what size if you don't know what gear ratio you're using, and you don't know anything about the output characteristics of your motor, because I've seen people do all sorts of weird things here. And Yeah, it looks pretty simple. Yeah, most of the time you can just throw it together because I've created a project where I want to see you succeed and not fail. But if you understand how we came about those decisions and how come your motor is going to work with the recommended settings, then when you move into a different environment and you're doing something with your students, then you'll be able to take a look and say, aha, I remember that miserable January where I had to sit down and figure all this stuff out, and I can't remember for the life of me how I did it, but I've got the notes somewhere, and well, I'm kind of stuck because I can't find the notes. Maybe I'll email Jason and buy him a beer sometime, and we'll figure out how to make it work. Anyway, you're going to figure it out now, and if you keep your notes, you'll be able to figure it out when it comes time for you to do it for real. Now, a couple of things you'll see on here. This chart is not labeled nearly as nicely, even though it is in metric, which is a vast improvement. But what we're looking at right here, you can see that we've got our speed coming up and down here, 5 to 15,000 on there. Our current, 1 amp, 2 amp, 3 amp, considerably less than the hundreds that we were looking at on that big 1 horsepower motor. Our efficiencies right here only comes up to 75%. Now, what are we looking at on here? I also don't see a power output on here. Okay, how do we know this? What's going on right here? Well, let's take a look right here. How can we figure out what some of these things are? Well, first of all, they give you a clue. N right up here is on the same column as your speed. This line looks like your speed coming down here. And remember, if you follow this line through, when you hit your maximum torque, okay, you're going to be at 0 RPM. And this line comes through and tells you that your torque at stall is going to be 3.53 Newton meters. So follow that line through down here and it would meet right down here. They haven't plotted it all the way down because they really don't want you operating the motor in this range. And if you're operating the motor in that range for too long, it is going to smoke. It's not designed to work in there, okay? And right in here, it tells you that your current at stall, follow that line up to there, is going to be at 2.1 amps somewhere right in here. Okay, so follow this down to where that line would meet up in there, but don't operate the motor in that range for any extended period of time. So IS right in here, stall torque 2.1 amps. Current at stall 2.1 amps, torque at stall 3.53 millinewton meters. Okay, so thousandths of a newton meter because we're talking really tiny amounts of torque coming off this motor. Thankfully, it spins fast, so when we gear it down, we can get some useful torque. But let's take a look at what this curve right here is. Now, if it was more symmetrical and centered at about 50% of your stall torque, that would be your power. But you'll notice that there's no power output listed on here, which is fine. We don't really need it. We're more interested in the RPM and the speed. And the efficiency right here. The efficiency of your motor is this funky little Greek N symbol. No, I can't remember my alphabet. Anyway, it's not a Greek N. We'll call it that. So we come right across here, and your very peak efficiency on here is going to be less than 50%. This is not a particularly efficient motor. It's not a bad heater, just a very low power one. So let's take a look on here and say, well, where do we want this motor to spin to get lots of power out of it? We're not going to get much efficiency at all out of it, but let's take a look at where we should be spinning that. Well, if you come to your stall torque, 3.5, okay, it's going to be down in here somewhere. Divide that by 2, and that'll give you 1.75-ish, which will be right in here somewhere. So basically about halfway along. There's our 2.5. You can figure out how many different steps there are, but somewhere right in here is going to be your peak power output. And then what you're going to see is that peak power output is going to come somewhere just under 1 amp of current, and at that torque load, your N right here for your RPM is going to come across as going to be spinning at about 7,500 RPM. And you can use that information and then say, well, what's my gear reduction in my little gearbox? You're going to have a Tamiya gearbox, probably not one of these yellow ones right here. So you actually get to build the gearbox and control what the gear ratio is. And then you can say, well, if I'm working with a really large diameter wheel, I'm going to need it can spin slower to get the same speed because 1 RPM covers a lot of distance with a big wheel. But I'm going to need a lot more torque to turn that wheel. And if you design your mini sumo with a smaller diameter wheel, then you're going to want it to be spinning faster at the output, and you won't need as much torque to make it spin. So all sorts of different ways to get different amounts of power out of your little gearboxes. And the motor power curve is an amazing tool for understanding that. And you're probably still sitting there going, lost ya 4 slides ago, Jason. And that's a beautiful thing about a recorded lecture. You can go back 4 slides and see what it's doing. And I have some questions for you on the Learning Hub where you can go through and make sure you do get a chance to understand what's going on with these. So there we go. Thank you very much for your indulgence with all my tales about motors and all this. And we will talk more about gearing. We will talk more about controlling them. We will talk more about calculating how to set everything up on here. I know you're looking forward to all that. But the motor power curve is where it all comes from. And the motor power curve derives from the basics of how the brush DC electric motor works. Brush DC permanent magnet electric motor works. Whew. It's New Year's Eve. I think I need to get cleaned up and go get a beer or something. Talk to you later.